Hello everyone. This time we're going to discuss integration and some applications. I am Catherine I. Merca from the Department of Mathematics and Statistics. Earlier, we discussed differentiation of functions. This time, we will be discussing anti-differentiation of functions. But the question is, does an inverse process of differentiation exist? For the answer, the inverse process of differentiation called anti-differentiation cannot always be performed. However, we can consider a set of functions for which anti-differentiation can be performed. For the outline of this presentation, we have the following. We're going to discuss the indefinite integral, the antiderivatives and formulas of anti-differentiation, and the integration by substitution. So in the second part, we're going to discuss later the definite integral. Recall that the process of anti-differentiation is just the inverse process of finding the derivatives of functions. Here we have the following definition. If we let capital F and F be two real valued functions defined on the interval AB, we say that the function f is an antiderivative or indefinite integral of f in AB if the first derivative of capital F is equal to f of x for all x element in the interval AB. Example 2 says that if we let f of x be equal to 3x squared for all x element in the interval 0, 1, then the functions f sub 1, f sub 2, and f sub 3 defined by f sub 1 of x equals x cubed, f sub 2 of x equals x cubed plus 4, and f sub 3 of x equal to x cubed minus 2 are antiderivatives of f since f sub 1 prime of x is equal to the derivative of x cubed here, but the derivative of x cubed is equal to 3x squared, which is actually equal to f of x. Similarly, we have f sub 2 prime of x is equal to the derivative of, since f sub 2 of x is x cubed plus 4, so we have derivative of x cubed plus 4, but the derivative of x cubed plus 4 is equal to 3x squared. And 3x squared is our f of x. Similarly, f sub 3 prime of x is equal to the derivative this time of x cubed minus 2, which is equal to 3x squared. Again, 3x squared is equal to our f of x here for all x element in 0, 1. Meaning to say, we made use of the definition, that is, if f is an antiderivative of f in AB, if f prime of x is equal to, so that's what we did here, we took f prime of x here, equal to f of x, and we'll come up with the original function f of x there for all x element of AB. Meaning to say, a function can have a family of antiderivatives. In fact, the function f defined by f of x equals x cubed plus c, where c is any constant, is an antiderivative of f. Theorem 3, we have the following. If we let f be an antiderivative of a function f on AB, and if g is also an antiderivative of f on AB, then g is equal to f plus c for some constant c here. In other words, if we have f and g are antiderivative of f, then f and g differ only by a constant here. So your f and g differ by a constant. Now, a process of finding the set of all antiderivatives of a function is called your anti-differentiation or integration. This is usually denoted by the integral sign there, which look like an elongated S. The set of all antiderivatives or indefinite integrals of f of x will be denoted by, you have this one, integral of f of x dx. In this case, this symbol here is your integral sign, and this one is what we call your integrand. Again, this is your integral sign, and f of x is your integrand. Now, if f is an antiderivative of a function, f, then we have the following notation, that is, the integral of f of x dx is equal to f plus c, such that c is a constant. For simplicity, we can omit the pair of brackets and write the integral of f of x dx is equal to f plus c. In this case, we have c there is your constant of integration. Now, we recall the following differentiation formulas. This, the derivative of x is equal to 1. Derivative of x with respect to x equal to 1. The derivative of x to the n with respect to x is n. You have n here, x to the n minus 1, where n is any real number. The derivative of, you have here a constant a times f of x is equal to, you can take out a outside the derivative sign and come up with simply the derivative of a times the derivative of f of x. And the derivative of a sum and difference would be, you can individually take the derivative of the function f of x here, plus or minus, it depends on the sign here. You can take again the derivative of g of x. Here are the theorems on anti-differentiation. We have here the integral of dx is equal to x plus c. And we have the integral of alpha of f of x dx is equal to, we can take out this constant alpha here outside the integral sign and come up with alpha integral of f of x dx. The integral of f of x plus g of x dx, you can individually take the integral of its function here and come up with integral of f of x dx plus the integral of g of x dx. As for the integral of u to the n du, where you have n is not equal to -1 and n is a rational number, you will have the integral of u to the n du is equal to u to the n plus 1 all over n plus 1 plus c. Notice that this time we added the exponent with 1, but we also divided this function here with n plus 1. As for the integral of 1 over u du, it's equal to ln of u, absolute value, plus c. So note that we have here ln of the absolute value of u. The integral of e to the u du is simply e to the u, so it's the same function here, plus c. The integral of a to the u, this should be du. Du is equal to a to the u all over ln of a plus c. Where here, u is a function of x, and a here is a constant. Here are the antiderivatives of trigonometric functions. We have the integral of sine u du is equal to the negative of cosine u plus c. The integral of cosine u du is equal to sine of u plus c. The integral of secant squared u, this should be du, is equal to tangent of u plus c. The integral of cosecant squared u du is equal to negative cotangent u plus c. The integral of secant u tangent u du is equal to secant u plus c. And the integral of cosecant u cotangent u du is equal to the negative cosecant u plus c. Now, how are we going to recall all these antiderivative formulas for trigonometric functions? Can make use of the following mnemonic device. Now, if you remember, we have actually tricks for memorizing the derivatives of trigonometric functions before. And how did we do that? We have the derivative of sine u is equal to cosine u du, and the derivative of cosine u is equal to negative sine u du. Why? Because we have to recall that we have this DCNS as a device, mnemonic device, wherein you have derivative of cosine dc, then you have negative sine u du. And the derivative of cosine, therefore, would simply be, the derivative of sine, therefore, would be cosine u du. As for the derivative of secant u, we have here secant, so we have the derivative is secant tangent. So you have there secant u tangent u dx. And the derivative of cosecant, we have negative cosecant cotangent. So we have there negative cosecant cotangent. And the derivative of tangent, you have your tangent there, is your secant squared. You have secant times secant. And the derivative of cotangent is, you have negative of cosecant squared. So you have this one. So these box here that we made use of earlier, we're again going to make use of this in memorizing the integral of trigonometric functions. So here's the trick for memorizing the trigonometric integrals. Note that u is a function of x. So again, we make use of these box wherein we have secant, secant tangent, we have cosecant, negative cosecant, cotangent. So we can first consider the double functions. What do we mean by that? We have the integral of secant squared, we have secant times secant, is tangent. Tangent u, let's see. The integral of cosecant squared, so this one, we have a negative sign, is now negative cotangent of u plus c. And then the integral of secant u tangent u, this one, integral of secant u tangent u is secant u. So you have this. And the integral this time of cosecant cotangent is your negative cosecant. So this one, the integral of cosecant cotangent is what is left here is your cosecant. Now, if we have DC and S, we also have what we call your SNICI. Your SNICI now stands for the integral of sine is negative cosine. So we have here, integral of sine is negative cosine of u plus c. So meaning to say, the integral of cosine, therefore, will now be positive sine. Integral of cosine is your positive sine. Now, how do we call this one? You have to memorize this. SNICI. Memorize also this one, cosine of u. And we can again relate this with the integral of tangent of u du. Recall that we have your this value here, tangent u. Then that is equal to ln. So everything here has an ln. Okay, ln of this time. This ln of secant u plus c can actually be derived by making use of the integral of, we know that tangent is our sine over cosine, right? So we can derive that one. But for simplicity, we make use of this formula, wherein we derive it from here. That is, we recall it, making use of this is SNICI. That is, integral of sine u du is equal to negative cosine u plus c. The integral of tangent now is the negative ln of the absolute value of cosine u plus c. And your integral of cotangent u du you recall that the integral of cosine u du is sine u plus c. So you simply put an ln there and you take the absolute value of sine u plus c. And that's how you recall the integral of cotangent. So you have cosine here. So you have your cotangent here. The integral of cotangent is the ln simply of this, whatever is the result here. So ln of sine u plus c. As for the double functions in integrals, they are actually added. What do we mean by this one? So if we have integral of secant u du, go back again to this one, integral of secant u, that will be ln, so we still have that ln there, ln of secant, absolute value of secant u plus tangent u. So you have ln of secant u plus tangent u, plus do not forget your constant. And the integral of cosecant u du, okay, from here we have cosecant, because there's a negative there, then you have ln of cosecant minus, we have cotangent. Absolute value, then you have plus c. So this box here, which we made use of as a mnemonic device in recalling our derivative of your trigonometric functions, is actually useful also in memorizing the trigonometric integrals. How about the integrals of inverse circular functions? Now, the formulas for integrals yielding the inverse circular functions are given as follows. That is, the integral of du over the square root of 1 minus u squared is equal to sine inverse of u plus c. The integral of du over 1 plus u squared is tangent inverse of u plus c. And the integral of du over u times the square root of u squared minus 1 is equal to secant inverse of u plus c. Now, if the constant 1 here in these integrals is replaced by some other positive numbers, one can use the following generalizations. That is, instead of a 1, we replace that with a. So you have now a1, the integral of 1 over square root of a squared minus u squared equals du. It becomes sine inverse of u, so you have your u here, over a. So instead of sine inverse of u only, you will have sine inverse of u over a plus c. Integral of 1 over a squared plus u squared du is equal to 1 over a tangent inverse of u over a plus c. And the integral of 1 over u times the square root of u squared minus a squared du is equal to 1 over a secant inverse of the absolute value of u over a plus c. So for example, we have, you're asked to evaluate the following indefinite integrals. That is, you're asked to evaluate for the integral of x to the 8 dx. So if you recall, we have the integral of u to the n du is given by u to the n plus 1 over n plus 1 plus c. Meaning to say, what are we going to do here? We can simply add 1 here when we evaluate this. Add 1 and divide it by that n plus 1. So that would give us the following. That is, the integral of x to the x dx is equal to x to the, you have 8 plus 1 all over 8 plus 1 plus c. So this now becomes, the integral of x to the 8 dx is x to the 9 over 9 plus c. We're asked to evaluate the integral of 3x to the 7 minus 4x to the 5 plus 3x to the 4th minus 7x squared minus x plus 6 dx. So similarly, we can make use of this formula here. So that we now have the following. You have 3x to the 7 plus 1, so you have 8. So over 8 there. Then 4, integral of x to the 5th, will now give us minus, we have a minus, so we still have a minus there. 4, so 5 plus 1, you have 6 there. So you have 6. Plus 3, then this one, x to the 4th, that becomes 4 plus 1, so you have 5. So 3 over 5, x to the 5th. This is a minus, you have a minus. So 7, and then you have 2 plus 1, that's 3. So you have x cubed over 3 minus, this is understood to have an numerical coefficient 1, that's why you have 1. X1, understood again to have an exponent 1, so you have, that becomes 2 because 1 plus 1 is 2, and you have here over 2. Plus 6, remember the integral of dx is x, so you have 6x plus, do not forget c, because we are on indefinite integral. Meaning to say, this now can be simplified as 3 over 8 x to the 8 minus 4 and 6 there. You can rewrite as 2/3 x to the 6 plus 3 over 5 x to the 5th minus 7 over 3 x cubed minus 1/2 x squared plus, we have 6x plus c. Next, we are to evaluate the integral of the cube root of x times the quantity 2x squared minus 7 over 3 times square root of x dx. So we can rewrite this. This can be rewritten as x raised to 1/3, and then you try to multiply it to this binomial, and then that's the time that you simplify. So we have the following solution, that is, again, you rewrite the cube root of x to be x to the 1/3. So you have 2x squared minus 7 over 3. Square root of x can be rewritten as x to the 1/2 dx. And then when you multiply this, what do you do with the exponent? You have this exponent 2 here is equal to 6 over 3. So that becomes 6 over 3 plus 1 over 3. That's why you have 7 over 3 here. As for this one, x to the 1/2, you can rewrite this as x to the negative 1/2 when you place it up there. So x to the negative 1/2, and then you have 1/3. You can take the LCD to be able to add up these two and come up with x to the negative 1 over 6, and your 7 over 3 is from here. So recall, again, what did we make use of? We made use of this formula. So that this now becomes 2 times x to the 2 over 10 over 3. Okay, when we try to integrate this one from this formula, integrate that, you now have 7 over 3, you add plus 3 over 3, you add 1. So, but what is plus 3 over 3? That becomes 10 over 3. So, over 10 over 3. This one, as for this, you add 1, so you will have plus 6 over 6. So, that becomes x 5 over 6, x raised to the 5 over 6. And you put 7 over 3 times the quantity 5 over 6, because you have originally 7 over 3 there. So, plus a certain constant. Then rewriting this one, 2 over 10 over 3 gives you 6 over 10, x to the 10 over 3 minus, rewriting this one, you have 42 over 15, x to the 5 over 6 plus c. That is, this one can be simplified. Your 6 over 10 can be rewritten as 3 over 5, x to the 10 over 3 minus, again, this one can be simplified as 14 over 5, x to the 5 over 6 plus c. Now for our next example, we have the following: the integral of 5 to the x dx. Making use of the formula, integral of a to the u du is equal to a to the u ln of a plus c. We have here our a is 5 and our u is x. We have du is dx. So meaning to say, we can take the integral as, since our a is 5, we have 5 here to the x, our u is x, ln of a, so ln of 5 plus c. For the next example, we have the integral of 9 secant x minus 5 cosine squared x all over 3 cosine x dx. Notice the divisor is a monomial. So we can actually take the integral first of 9 secant x all over 3 cosine x minus the integral of 5 cosine squared x dx. That is, you can have the following. You have is the integral of 9 secant x all over 3 cosine x dx minus this one, which is the integral of 5 cosine squared x all over 3 cosine x dx. Now recall that your cosine x is equal to 1 over secant x. This is an identity. So your cosine x here can be rewritten as 1 over secant x. Notice that we have a secant x up here. And 9 over 3 is actually equal to 3. So that we can now rewrite this as 3 times secant x all over 1 over secant x dx, its integral. And then from here, notice that you have cosine squared and you have cosine x. So you can divide out the cosine. You are left with the integral of 5 over 3 cosine x dx, and you have a minus because you have a minus here. Now, this one, you can take out the constant to come up with 3 integral of secant squared x dx minus, you have 5 over 3 cosine x dx. So you can again take up the constant here, integral of cosine x dx. And if you recall, we have the following formula for the integral of secant squared u du, which is equal to tangent of u plus c. Also, we have the integral for cosine of u du is your sine u plus c. So because of these formulas, we will have your integral of 3 secant squared x dx is now equal to 3 tangent of x minus, we have 5 over 3 here. So integral of cosine is sine. So you have 5 over 3 sine x plus c. So we have the following as your answer here. Now, for the integration by substitution or change of variable, we have the following theorem, which says that if f is a differentiable, if g is a differentiable function on AB and n is not equal to minus 1, it's a rational number, then the integral of g of x to the n, g prime of x dx is equal to g of x raised to the n plus 1 all over n plus 1 plus c. For example, we are asked to evaluate the following indefinite integral. That is the integral of the square root of 9 minus 5x dx. So for the solution, we let u to be equal to this one, 9 minus 5x. So inside the radical sign. Then if we take du, the derivative of 9 is 0, but the derivative of negative 5x is negative 5 dx. We can divide both sides by negative 5 to come up simply with dx. So you have dx equal to negative 1 per 5 du. So make use of substitution, and we come up now the integral of square root of 9 minus 5x dx. Okay. Since our dx is replaced by negative 1 over 5 du, then and our 9 minus 5x is replaced by u. So you now have square root of u du minus 1 over 5, its integral. So that's equal to, because this is a constant, you can take that out of the integral sign. Then you have negative 1 over 5. U to the, this square root can be rewritten as 1/2. It's u to the 1/2 du. So recall the theorem that we had given earlier, that is the integral of g to the x to the n, g prime of x dx is equal to g of x to the n plus 1 all over n plus 1 plus c. So this is u to the 1/2 du. To say, that's equal to negative 1 over 5, so this one, u to the, we have, what do we do? 1/2 plus 1. Plus 1 can be rewritten as 2 over 2. So we have 2 over 2 plus 1 over 2 will give us 3 over 2. And this one, your n plus 1 is 3 over 2 plus c. Or simplifying further, you can rewrite this 3 over 2 there as times 2/3. So we have negative 2 over 15 u to the 3 over 2 plus c. Or you can go back now to the original value of u, which is 9 minus 5x. So it becomes minus 2 over 15. Replace your u there by 9 minus 5x raised to the 3 over 2 plus c. So our next example is we're asked to evaluate the integral of 3x cubed plus the quantity 2 plus 6x to the 4th raised to the 5th dx. Now what do we do here? We let u be equal to the quantity 2 plus 6x to the 4th. Then, if we take the derivative of u, that is, the derivative of 2 is 0, derivative of 6x to the 4th is 4 times 6 x cubed dx. But if you notice from here, what do we have? We have 3x cubed dx. So we have to do some mathematical tricks here to be able to get your 3x cubed dx. And how do we do that? We can rewrite this one, du equals 24x cubed dx to be equal to 3x cubed dx equals 1 over 8 du. Why? Because your 8 times 3 is actually still equal to 24x cubed. And we know that we need only 3x cubed dx here, 3x cubed dx, and not 24x cubed dx. So we have now rewritten 3x cubed dx to be equal to 1 over 8 du, and we can substitute this value now into the following. That is the integral of 3x cubed, the quantity 2 plus 6x to the 4th, closed quantity, raised to the 5 dx is now equal to, replace your 3x cubed dx, this one, by 1 over 8 du, and then this one, 2 plus 6x to the 4th, that is supposed to be your u, so you replace it by u, raised to the 5th, so you have raised to the 5th, is equal to, you can again take out this constant here out of the integral sign, so 1 over 8, integral of u to the 5th du, okay, so when we take that one out, we come up with this, equals 1 over 8, make use again of the formula for anti-differentiation, that is, you have 5 there, so we add 1, so you have u to the 6, all over, you have again 6, plus the constant c. So we now have 1 over 8, but times u to the 6 over 6, that will give us 1 over 48, u to the 6 plus c. But you have to go back to the original value of u, which is 2 plus 6x to the 4th. So you have 2 plus 6x to the 4th raised to that. This one is 6 plus c. And that's your answer. As for the next example, we have the integral of the quantity 3 sine 3x minus 2 times the square root of sine square root of x dx. So note that the integral of 3 sine 3x minus 2 square root of x sine square root of x dx can be rewritten as, you can take the integral of this minus the integral of this one dx. So you have 3 sine 3x dx minus, you can integrate that one separately, 2 over square root of sine square root of x dx. Now, for this one, if we let u be equal to 3x, and this one for v be equal to square root of x, then our du here is 3 dx. And dv is 1/2 of, remember that if this is your v, then if you take the derivative of this one, this is actually x raised to the 1/2. So the derivative will now be 1/2 times x to the, okay, so you multiply the exponent, and x to the n minus 1. So you subtract minus 2 over 2, that's why you have negative 1/2 dx. Or you can rewrite this one as 2 dv, so 2 dv equals 1 over square root of x dx. Why do we do that? Because we actually have here your 1 over square root of x dx here. You have your 1 over square root of x dx here. So by substitution, we have 3 sine 3x. the original one, 3 sine 3x dx, minus integral of 2 square root of x sine square root of x dx will now become sine of u du. Okay, because our du is 3 dx, so you have 3 here times dx, that's your du, and our u is 3x here, 3x, so we have sine u du, minus integral of 4 sine v dv. Why? Because we have here your 2 dv is equal to your 1 over square root of x dx. So your 1 over square root of x dx is equal to 2 dv times 2. So you have 4 dv. And then you have sine square root of x is your sine. Our v here is equal to square root of x. So you have sine v. Then we can easily get the integral of sine is easy. The integral of sine is negative cosine of u, plus we know that the integral now of sine is positive. Integral of sine is negative cosine again, but we have a minus. You can take out 4 of the integral sine, so minus of minus, that's why you have 4 cosine of u plus c. Meaning to say, you have to go back again to the original value of u, which is equal to 3x, so negative cosine of 3x, plus 4 cosine of, again, our v here is equal to square root of x, square root of x plus c. Now for our next example, we're asked to evaluate the integral of x over 9 plus x to the 4th dx. As for the solution, we can let u be equal to x squared. Notice that this is 9 is actually the square root of 3, and x to the 4th is the square of x squared. So we can rewrite this as u equals x squared, so that your du now becomes the derivative of this, which is 2x dx. And we can rewrite x dx because we only have x dx here. X dx to be equal to 1/2. You can divide both sides by 2, so you have 1/2 du is equal to your x dx. Now by substitution, we can have integral of x all over 9 plus x to the 4th dx is now equal to, you have x dx, so you have your x dx there, then 9 is replaced by 3 squared, x to the 4th is rewritten as x squared squared, so we now have 1/2 of the integral of du, because your du x dx is replaced by 1/2 du, and we have 3 squared plus x squared squared. Can you recognize this one? We recall the following integral values, that is integral of 1 over a squared plus u squared du is equal to 1 over a tangent inverse of u over a plus c. So that from here, our a here is 3, so it's raised to the second power. When you have u there, raised to the second power. So from that formula, you can compute for the integral of this. It will be 1/2 times, we have 1 over a, since our a is 3, so you have 1/3 tangent inverse of u over a, so our a is 3, so u over 3 plus c. Or if we simplify this, it becomes 1 over 6 tangent inverse of, again, our u earlier is x squared. So you have x squared over 3 plus c. Now we go to the last example in this presentation. That is, we are asked to evaluate the integral of 1 over the square root of 4 minus 9x squared dx. So for the solution, notice that here we have your 4 is actually rewritten, or can be rewritten as 2 squared, and our 9x squared can be rewritten as 3x, the quantity squared. So if we let u be equal to 3x, then our du now becomes 3dx. But then if you notice, you only have dx here, so we can divide both sides here by 3 and come up with 1/3 du is equal to dx. So by substitution, we have the integral of 1 over square root of 4 minus 9x squared dx is equal to, we have 1 over the square root of, your 4 is replaced by 2 squared, minus 9x squared is replaced by the quantity 3x raised to the second power dx. And then, because we have our dx is 1/3 du, so you have 1/3 here du, then square root of 2 squared minus our 3x is our u, so that becomes u squared. And if you recall, the integral of 1 over square root of a squared minus u squared du, so we're in our a here is 2, and our u is 3x, that's equal to sine inverse of u over a plus c. So that that is now equal to 1/3, okay, sine inverse, yes, we have a 1/3 there, sine inverse of u, our u here is equal to 3x, so we have 3x, and our a is 2. So you have 1/3 sine inverse of 3x over 2 plus c from this formula here. So do not forget, now recall your differentiation formulas, because we know that your integral is simply your anti-differentiation. I mean to say integral is simply the inverse process of your differentiation. So do not forget your differentiation formulas, which is given as follows. Again, how do we recall for your derivative cosine, which is equal to the negative sine u dxu, that's your dcns. And to be able to, that is derivative of cosine equals negative sine u d c n, we have s there. And then is nisi, to say the integral of sine is negative cosine. It's a reverse process. As for derivative of second, that's equal to, again, what do? You remember the box that you have earlier. The second tangent, cosecant, negative cosecant, and you have your cotangent. And with that in mind, you'll be able to recall up to these 6 formulas here for your differentiation, as well as for the formulas for your integration. So we'll end up with this slide, and the next part will be discussed on the next presentation.